we can graph a radical function much like we do any other function, just by, as we did in the last video, evaluating, plugging some numbers in, and figuring it out. And one of my points in the last videos was that using values which produce perfect squares is kind of easier because it will result in whole number values a lot easier to graph, say, on a grid, than if we just plug in random numbers and get irrational values. It's not as easy to graph. So let's say, for example, we wanted to create the graph of f of x here on the packet, which is defined to be the square root of x plus 1. Here, again, we could just sort of pick whatever values you want. If we're looking at our grid, we could check every value from -10 to 10, but not all of those will work, and a lot of those will result in some strange answers. But what I kind of recommend is, if we start kind of like looking at -7 in the previous example, if we start with a 0, that's going to give us the starting point for that radical function. In this one, it would be -1, because -1 plus 1 would be 0. And that's going to always be the basis for the domain of this function. And, basically also another one that would work very easily is 0. Because if I plug in -1 into f of x, that would give me the square root of 0, which is 0. If I plug in 0 in here to f of x, I would have 0 plus 1. Square root of 1 is going to be 1. And so those are some pretty easy starting points to work with. And, say I was to increase it, like let's just say, for example, I plug, I'm just going to plug in every value on the graph, 0, 1, 2, 3, 4, 5, 6, 7. Well, my point is some of those we may want to skip, because like if I plug in 1 here, this would give me the square root of 1 plus 1, which is of course 2. And 2 is a number which is not a perfect square. And as I was saying in the last video, when it's not a perfect square, it's going to result in an irrational number, something which is not easy to necessarily understand, but it's going to be kind of an awkward number. We could always approximate it and still use the approximation to what is square root of 2 approximately equal to in our graph. But what I think it's just easier to skip over those values and move ahead to the next perfect square. The next one that would be really easy would be 3, because if I plug in 3, 3 plus 1 is 4, and the square root of 4 is of course 2. And jumping ahead to, well, what's the next perfect square? If you know your perfect square is 1, 4, 9, 16, 25, basically just each number sequentially squared, that can help with, with graphing these and determining the easy points to put on your grid. So next up would be 8, because 8 plus 1 is 9, because 9 is the next sequential perfect square. And that would leave me with 3. And basically, once I have a handful of points, I can just plot them and graph them in order to get a sense of what my radical, I keep doing that, radical function looks like. But also what I wanted to mention is, well, why didn't I check to the left of -1? Why didn't I check, say, for example, -2 or -3? But the issue with square root functions and graphing is that if I plug a negative into this, what I'd be left with the square root of -2 plus 1, which is the square root of -1. And one of the key problems with square roots and as the function in general is that if we're trying to figure out, the whole point of it is to figure out, well, what number squared makes the inside, which of course in the case of 4 is 2. But when it comes to negatives, this was a historically difficult problem, because obviously there is no real number. There's no numbers that you can square to get to a negative, right? Because whenever you square a number, say for example, I said the answer was -1. Well, -1 squared is not -1, it's +1. And same with +1 squared is 1. Basically, any number squared must be positive. So the square root of a negative is something, well, historically it was called impossible. There was no way of doing this because it just doesn't work. But as over time, what we've learned is that technically there are ways to get a square root to be negative just by what we refer to as imaginary number system. And now imaginary numbers are actually a misnomer. This is something you probably remember from algebra, is that the square root of -1, we often define this to be I, the imaginary unit. But for right now, we're just going to say that this is not real, because no regular, in math we just refer to them as a set of real numbers. No real number can square to be negative, but there are numbers that exist that actually do work for this. But non-real numbers will not show up on the graph, and non-real numbers will not be part of the domain. So all this kind of is a way of saying, for now, we're just gonna kind of skip this, and everything that produces a negative is going to produce values that are not within the domain of this function. But basically, anything above or to the left of -1 is just going to not be part of our graph. So we don't even need to bother because it's not going to be part of the domain either. But if we graph the points that do work, for example, -1, 0, 0, 1, 1, 1.4, just all the points I found, 3, 2, and 8, 3, we can kind of get a sense of how this graph will behave. And basically what ends up happening is it results in a sideways half parabola. And actually we're going to talk more about parabolas in chapter 8 when we talk about quadratic functions and the quadratic formula, which is why we're doing all this stuff in this particular order. There's a lot, we're not just kind of talking about random things. All of math kind of builds upon itself to get to a more complex idea. And the quadratic formula is one of the more important things that we're going to get to in this class. But that being said, anyways, it has a very distinctive shape. It kind of looks like a half of a rainbow, if you want to remember. But all radical functions, well, when they're square roots, will have a graph that looks somewhat like this. And discussing the domain and range, once we have a graph, it becomes a lot easier to see what this would be. In this particular graph, the domain appears to be from -1 to infinity, basically being that the first point I had that worked was the 0 value of -1. And then in between, basically, and I could have plugged in any other number. And I chose specifically to plug in specific numbers that made this easy, but along the way they would form this trending behavior. And as you take the square root of larger and larger numbers, it will grow. But because the square root actually kind of compresses the value, it's not a straight line, it kind of gets smaller and smaller. Well, the speed at which it grows gets smaller and smaller, that is, as a way of saying. And also another thing that we can notice from the behavior of this is that the range of square root functions is in their baseline form is 0 to infinity, because square roots can only produce positive answers. If I look at all my outputs here, I only get positives. It's never going to produce negative results just by the way it works. And technically, when we refer to a square root of a number, what's actually kind of misleading is we often say, as I just said, the range is positive, 0 to infinity. It can't be negative. But technically, square roots of a number is a more basic definition. So a radical function, by definition, is, as we're defining it, the positive root of a number. But technically, all numbers don't have one root. All numbers actually have two square roots. Like, say I was thinking about 4, and I wanted to know what is the square root. Technically, all numbers have two square roots always. They only have, most people would often think, well, if I'm thinking about what is the square root of 4, I would think about rad 4. And rad is just a shorthand for radical, but rad 4 is just, is 2. 2 is because 2 squared is 4. But technically, when we refer to the square root, the radical function is not equivalent, because actually all numbers have multiple square roots. Obviously, 2 squared makes 4, and that is one of the square roots of 4. But there's always a secondary root, square root that is, to a number, which in this case, -2 squared also makes 4, obviously, because as I said before, whether you square a positive or negative results in a positive in either form. So by definition, 4 actually has 2 square roots, both positive and -2. We usually don't think about this because because the radical itself only returns the positive square root, which is, again, kind of why I'm talking about this here. Why the range is 0 to infinity, because we have two answers, and with a function we can't have two answers. So we basically when we're talking about a radical, we're only referring to the positive square root because we need to have one output rather than two. And basically it makes sure that it's a function, because the square root is not a function because there's always more than one answer. There's always two square roots to any number. And actually the same thing applies to cube roots and fourth roots and fifth roots. There's actually always 3, 4, 5, and 6 cube root. There's 3 cube roots to every number, 4 fourth roots to every number. That's something that we're not going to even come close to talking about in this class because it gets kind of complicated in finding. But it's quite an interesting algebraic property that a lot of people don't know about. But anyways, that's kind of the differentiation between a root and a radical. Really, the radical is just the singular answer. And when we talk about cube roots and fourth roots, really, again, these are radical functions. It's only we're always finding what we call the primary root, not the secondary or tertiary in the case of, say, a cube root. And actually, to circle back to this example, one last thing I wanted to mention is, let's say we wanted to find the domain. There's actually a much simpler way to find it without having to graph it. And that's that it's reliant on the basic property that the inside of the square root has to be, it can't be negative. When it's negative, it produces imaginary answers. When it's 0 or larger, it works just fine, regardless of the number. So basically, the way that you can solve the domain of any radical function is you can always set up an inequality, take the inside and set it greater than 0. So in this case, the inside, the radicand of this function f of x is x plus 1. Basically, if I take that and create a new inequality greater than or equal to 0, this will always reflect the domain of the function. And then if I subtract 1 from both sides, what I'd end up with is x is greater than or equal to -1. And that is exactly the domain of the function always. So by rule of thumb, let's say, for example, with g of x, you want us to know what's the domain. Like what number, and so again, why we care about this is if I want to know what number should I be plugging into this function to graph it, well, you can always start by finding the domain in the same exact way. Take the inside, set it greater than or equal to 0, solve for x. So to solve for x here, I would be adding x to both sides, and this would leave me with 2 greater than or equal to x. Or, again, I could rewrite that as x is less than or equal to 2, but this would imply that the domain of this function is all real numbers less than 2. And so for this one, I don't want to be plugging in 3, 4, or 5, because again, obviously that would result in negatives. More of a common sense approach that you could take here is, well, what makes this negative? Don't plug it in. Only plug in numbers that make it positive. But if you wanted to know, well, what sorts of numbers should I be starting with? That's where the domain could come in handy. And once I've kind of found the domain, I could sort of pick and choose, well, which values do I want to plug in within there? And you never want to, go past 2, because anything beyond 2 will be imaginary. But I could say use 2, 1, or again, trying to pick numbers that result in perfect squares. So I'll just go ahead and write some of the ones that work out very nicely. But if I plug in 2 here, this would give me rad 0, which is 0. If I plug in 1, that would give me rad 1, which is 1. Plugging in -2, also since it's got a minus already in there, 2 minus a negative would become plus, and that's why negatives actually work just fine in this g function. So this would result in 2 plus 2, which is of course 4. Square root of 4 is 2. And 7, again, because it's 2 minus, really will become 2 plus 7, which is 9. Square root of 9 is 3. And so how I determined these numbers was I just sort of figured out, well, which ones produce whole numbers, just kind of the easy ones. But of course, you could plug in all numbers less than 2 and graph every single one. But this is kind of like the shortcut, easy way of finding a lot of those key points. And of course, I'm going to have an x-intercept of 2, 0. I also have 1, 1, -2, 2, -7, 3. And this square root function will have the same shape, just be going the opposite direction. Sorry, my phone keeps being noisy. But basically, we get a very similar shape going the other way because of the negative x. And of course, other sorts of math within the function itself can cause the shape to do the things, which is what we refer to as transformations. But anyways, that will summarize kind of our talk on the graphs of root functions, domain, range, and etc.